Hello and welcome, chemistry students. This next lesson is about the combined gas law, and we'll also look at what standard temperature and pressure mean. So we've now looked at several gas laws, and we're going to combine two of them into what's called, of course, the combined gas law. So just a review of some of the properties here, rather some of the laws, two of them that we recently looked at, Charles and Boyle's laws. We know the following couple of points here. So pressure, we know that pressure is inversely proportional. So it's proportional to the inverse of volume. And we also know that volume is proportional, directly that is, proportional to temperature. Right, and that created a couple of graphs that looked like this, and we went over these details in a previous lesson. Right? Now we can combine this, and we're not going to worry so much about the derivation, but this is essentially the beginning of that. I'm not going to expect you to derive the combined gas law, which is right here to the left. But it's these relationships that allow for this combining of these two laws to create, again, the combined gas law. Right? So not so original name, but suitable. We get P1V1 over T1 is equal to P2V2 over T2, where P stands for pressure, V, of course, stands for volume, and T stands for temperature. Okay, so our first example. So here we have a sample of gas occupying 500 milliliters at 40 degrees Celsius, right? I'll talk about units in just a bit. And 955 kilopascals is transferred to another vessel. Okay, so this is our second scenario here. It's transferred to another vessel at a lower temperature, right? And also at a lower pressure. Okay, we're gonna stick with standard units of measure. So we're going to have to convert milliliters then to liters, and we're going to convert Celsius to Kelvin, degrees Celsius to Kelvin, right? And this is at kilopascals, so we'll leave that at the correct unit here. Okay, so let's write down what we are given. So our first pressure of that first scenario is 955.0 kilopascals. Our second pressure of the second scenario here is 750 kilopascals. Right. First scenario's volume has 500 milliliters, and we're going to convert that to liters, and that's just 0.5 of a liter. Second volume is what it is asking us for. It's our unknown. Right now, off to temperature. Our first temperature is 40 degrees Celsius, but we know that we're going to convert that to Kelvin. So we add 273, and we get 313 Kelvin. Now our second scenario has changed. It's 0 degrees Celsius. But to convert that to Kelvin, we again add 273, and we get 273 Kelvin. Okay, so this is all the information we have converted to the necessary units. Now we can use P1V1 over T1 is equal to P2V2 over T2. Now let's go ahead and just rearrange. Now, don't forget, you're going to cross multiply, just a little bit of grade 9 math here. Cross multiply and solve for that unknown variable. In this case, it's V2. So that gives us P1 V1 T2 over P2 T1. Now, if transitioning from here to here is a bit of a task, let me know and I can review that with you. Okay, so post questions there, send me a message. All we're now doing here is just going to plug in all of our values for P1, V1, T2, P2, and T1. So bear with me, I'm going to write these all down with their correct units. And you would just plug this into a calculator and you're done. Okay, you plug it into a calculator and you get 0.555 liters. It says what is the volume in liters, right? So we're going to leave it like that. You could convert that into 555 milliliters, but it's not asking you to do that. It's asking you to leave it in liters. Now let's look at our sig figs here. So we really just see that there's 1 sig fig here, 1 sig fig here, 1 here as well. So we would just need 1 sig fig. So we've gone over how to round. This will round in our class, will round up to 0.6. 0.6. There you go. Okay, so that was the combined gas law. And I was just adding something here. It's important to, when you're especially working with gases that are affected, as we know, by certain variables, right? So certainly affected by pressure, also affected by temperature. So if these change your environment and therefore change certain variables, to study this, it helps to come up with a certain standard. Now think of this standard as in your own world, perhaps think of sending a file to someone, emailing it, sending a link to a file. Now usually that's not too difficult. That's because these file types have been standardized. It can be a .doc file or an XLX file, I believe is the name of that. It can be a Google Doc. Those certain files are common. They are standardized. But if it was some other type of file that no one's ever heard of, and you just wouldn't be able to open it. So to talk about this and to be on the same page from one lab to the next, one person to the next, it helps to have a certain set of standards. So here they are. Our first standard is standard temperature and pressure, also called STP. Now whenever you see that or read that, it just refers to 0 degrees Celsius or 273 Kelvin and 101.3 kilopascal, which is the pressure of the atmosphere at sea level. Okay, now another standard that is often easier to reach in a lab is standard ambient temperature and pressure. So roughly room temperature, 25 degrees Celsius, which is 298 Kelvin, and at 100 kilopascals, because we all don't live at sea level, although it might be nice. Okay, so these are those two standards. So whenever you see STP, it's implied that you have a temperature of 0 and a pressure of 101.3, SATP, 25 degrees Celsius, and 100 kilopascals. Okay, second example. So here, a chemist may find that a sample of gas occupies a volume of 43.4 milliliters, right, at a pressure of 973 kilopascals. Okay, so let's start writing this stuff down. Our P1, right, we just mentioned that here. Our initial pressure is 973 kilopascals. And our initial volume, we can write that down as well. Our initial volume is 43.4 milliliters. We might as well now convert that to liters. Right. Okay, all of this exists at a temperature of 27 degrees Celsius. So very good. 27 degrees Celsius, we're going to add 273 to that to give us the Kelvin measurement of 300 Kelvin. Okay, and then it says, what is its volume? Okay, so we don't know the volume. What is its volume at STP? Now, STP tells us temperature and pressure without actually saying it. So our temperature, our T2 in other words, is 0 degrees Celsius, which we know to be 273 Kelvin, and our pressure is 101.3 kilopascals. Good, so this tells us these are our STP conditions, Now we use the same combined gas law, P1 V1 over T1 is equal to P2 V2 over T2 to solve for our unknown. In this case, again, it's V2. So that is P1 T1. Let me make sure this is correct. P1 T2, not 1, and V1 over P2 T1. Okay, now bear with me again as I plug in all of our known values. (273 Kelvin) over our second pressure, which is 101, that's STP, 101.3 kilopascals, and 300 Kelvin, our initial temperature, our T1. So plug that all in and we get 0.379 liters. Okay, so what is its volume at STP? In this case, the question doesn't tell us to leave it at liters or milliliters, so you can leave it right there at liters, or you can convert to 379 milliliters, whatever you'd like. Either answer would be accepted, but again, we go back and look at our sig figs here. We have 2, so we can round this to the correct sig fig, so it would just be 2, so it'd be 38. 0.38 liters as our correct answer. Okay, so that's it for our 2 examples. Your home fun, a couple of things to remember. You have a worksheet posted online called the Combined Gas Law Worksheet, just for some practice here. Ask any questions as they come up. Also, don't forget to do your online practice check-in quiz. Again, this is not for marks. It's just an online quiz that will tell you the answer right after you finished it to see where you're at, and also lets me know where you're at too. Hope this helps.